So, the very last thing we did last time was I sort of tried to lay some groundwork about what we're about to get into. So you might not think that finding the area of something would be a difficult problem that would require higher level mathematics, correct? So for example, if I said, let's see, find the area of this triangle, right? Can you do it? Can you find the area of the triangle? Okay, I love it. So you guys are like, yes, Jeff, I can do it. All right, so what's the area of the triangle? 1/2 the base. How big's the base? 2. And what's the height?
3. Oh, 2.
Good job.
That looks a bit over 2.
All right. Realize I'm right up on top of it, so give me a little board license. All right. Everything's going to be this way to me, or to you. So this is 2, whatever the units are, right? But the minute that I instead give you something like this, and I say find this area, is that as easy? Nowhere near as easy. Could we guesstimate the answer? How would you estimate the answer here? Yeah, you could kind of do this, and then the answer would be 2. That would be an estimate. Is our estimate too low or too high? Too high? Too high? Too low, because we left out all of this. We included a little more than we needed to, but we left out a lot more that we should have included. Are you guys kind with me? Okay. So that's the fundamental idea here is we want to develop a way to estimate the area that we can then do a little calculus to and make it tell us the exact area, right? So we want to start with allowing ourselves to be close, estimate. But then we want to see, can we make this better? And I kind of talked a little bit about how we're going to make the estimate better last time. So the problem, so let's kind of do the first couple steps and then realize we have to stop and talk about a certain something. So let me ask you this. If I wanted to use, so what we talked about last time was using, oh my God, Blue, you are ready. Using rectangles to approximate this area, right? We actually could use any shape that's easy, but rectangles kind of win as far as figuring out areas of things. Hey, I was like, all right.
I made it seem like I saw what's on the board and just left.
I was like, all right, whatever, it's up to you. Okay. For those who just came in, I'm kind of catching up with what we said at the end of last class. We can estimate, we can get this area exactly, and we already did. But then when we have a question like this, much harder. The best we can do is estimate. Now this one specifically, I could estimate it with one big triangle, right? But in general, what we're going to do is we're going to use rectangles. So there's a few considerations for this. So here's the idea. I could use one big ass rectangle to estimate this. And there's a way you can, all right, does everybody agree that this function is really, really simple? I like it. So there will probably be shortcuts for this kind of problem that we can apply to this kind of problem. Are you guys with me? Okay. Can anyone tell me how tall of a rectangle would actually be like a crazy good estimate of this area? I mean, do you understand? So I could use one big ass rectangle like this. Why would that be not the greatest estimate if I use this here, which would actually be a square, but a square is a rectangle, so lay off, right? So what's wrong with this big ass rectangle here? It would be it would be a way big overestimate, correct? And so do you see how I want you to start picking up on a few things to consider? I could use 1, 2, 3, 18 billion rectangles, anywhere in between. Keep going above that, go to infinity, right? I can use how many rectangles? And the more rectangles I use, the better the approximation gets. But the key thing is, how tall will each rectangle be? What's gonna govern how tall the rectangles are? Why did I make it this tall? Why didn't I make it this tall?
Because the last point is then.
Yeah, I based the height on the right end of the rectangle itself, correct? Now, I could also base the height on the left end. Now, what would that do for me? Then the rectangle would look like this. It would be the rectangle of area 0, yes? So is that a good choice here? Now, real quick, is one rectangle a good choice in general? Probably not. In this case, is everybody semi with me? I've got I'm trying to work up to the point where we can estimate this area using rectangles like this. So, and I can find each of these rectangles areas really easy. And do you see, if I use this many rectangles, if I found the area of all these rectangles and added them up, wouldn't that be decently close to the actual area? How would I make it better? Add more rectangles. And that's the same thing as increasing the resolution. Yes? So I might say that phrase sometimes, and I want you guys to know what I mean. I'm just increasing. It's sort of like, how do you increase the resolution in your monitor? You get a monitor that has more pixels, right? Which is basically the analog to rectangles in this case. Okay. So this is one big ass rectangle. This is like the days of Nintendo or something, right? Big ass 8-bit thing. Can somebody tell me what do you think the best point, definitely not the left end point, gives me 0 area. Definitely not the right end point. That's a big time overestimate. So what's the best point to base my rectangle height on? What do you guys think? Sort of gave it away. It's not the left side. Yeah, the middle. If I make a rectangle this tall, take all this other shit away. Go. And I get this area. Can you see that this amount that I count over is exactly the same as the amount that I don't count? It's sort of like I take this rectangle and I put it here, right? So in this case, again, I really want you guys with me on this. This is a stupid, simple function. I don't even need calculus to figure out the area, so it's already a shortcut way to do it. So if I try to use rectangles, I probably don't. In fact, I only need one rectangle. What's the area of this rectangle? Careful. What's the area of this rectangle?
2.
Yeah, it's always be careful. Isn't this 2? 1, so the area is also 2. Yeah. And that, again, is because the function is stupid simple. Yeah? When we get functions like this, holy shit, I'm going to need some more help. I'm going to need more resolution, yes? Maybe? So what did you just figure out? When I am drawing rectangles, I need to make a decision on what's going to govern how tall they are. Now, obviously, the height's going to be based on the function height at that point. But am I going to use the left side or the right side? Right? If I use the left side here, I get flat. If I use the midpoint, I get this. If I use the endpoint, I get this. The right end. Yeah. Okay. I got to do this every now and again. Left, right. Okay. So, all right. Let's do this. Let's do this. Let's start to set up a problem. Let's take a more interesting function. X squared. So let's graph this thing. Let's see. little more room. 0 to 2. All right, so just graph the part that matters here. I'm not going to graph this part, it doesn't matter. I'm not going to graph past 2. So 0 is 0, 1 is 1, 2 is 4, and there's our nice parabola. What is so I want to find the area under f of x from 0 to 2. I don't know why. I just spelled under with 3 letters, but I did. You guys with me? So the fundamental thing that what we're creating right now does is it finds the area under any function I give it. The same way that the derivative process we created finds the slope at any point for any function I give it, right? Okay. So can you shade in what area we're about to try to find? Really lightly. Shade it in really lightly. What do you think? If I do this, I'll want this here. Now that is a little bit worse than this because it's curved, right? And it's actually kind of decently curved. This goes 2 over while this goes 4 up. Right? So if it was a straight line, it'd be 4, 4. Very different. Okay, maybe. So how many rectangles do you guys think we should use to try to do this? A lot. Do you think we need like a lot? Like when you say a lot, you're talking to a math guy, so that means 1,000.
You said like 4.
4, okay. All right. 4, and again, so we're starting to feel out the part. So everybody understands the basic idea. We're trying to use rectangles because rectangle areas are easy as shit. And I can just tell if there's an overestimate or an underestimate, correct? Okay, I like it. And the more rectangles I use, the better it should be. But the nicer the function is, the fewer rectangles I can probably get away with. Crazy nice, one freaking rectangle did the job, right? Okay, so let's say we want to use 4. So n is 4. Oh, crap, I need you up. How are you doing? I think you're dead, aren't you? Yeah, you're dead. Okay. Fantabulous. Come here, Blue. N equals 4. That means 4 rectangles. Become a thing. All right, I like it. Now the question is, how are you going to draw them in? What's going to determine the height? So I could basically do 3 different ways. So there's 3 options for us. I could do left endpoint, right endpoint, or midpoint. We're going to do, remarkably enough, we're going to do all 3. Just, of course we are, right? Okay. Does everybody get the idea? The idea is almost too nice to believe. Now, of course, in the next section, it's going to become what you probably would expect. Because what do you think we're going to do in the next section to make this as perfect as it can be? Okay. Be more specific. What did we say to do to make this a better estimate? Make n bigger, right? And what's the biggest we can let n be? We can allow it to go to infinity. So we're going to do the entire process, but then we're going to take the limit as n goes to infinity. Because whatever answer we get then is the exact answer. It's not an estimate anymore. If I get infinite resolution, I'm golden. You guys with me a little bit? All right, okay. So the nice thing with 5.1 is it's going to be very concrete. We're not letting anything go to infinity. You can actually draw on the rectangles. You can see exactly what the shit's going on. Okay. So let's do left endpoint first. Now let's figure out, first thing you're gonna figure out, I'm gonna use 4 rectangles, correct? Where are they gonna sit? Like where, it's gonna go from 0 to what? Where would the first rectangle go? How did you figure out, somebody, you guys see, when you go to the 1/2? How do we figure that out? How do we figure out how wide the rectangles are going to be?
It's half the first rectangle.
See it?
After the first rectangle, I guess. So I guess like, you know, the ones right there's actually one rectangle, but half of that.
Well, it's not always gonna be that. There's something about how far we gotta go and how many steps we're gonna take.
2 divided by 4.
Yeah, so it's gonna be, so we're gonna call the width of each rectangle, we're gonna call it delta x. Doesn't that make sense? That's basically how much x is gonna change each time we step. Okay, so that symbol makes sense. Delta is change in x, kick ass. And this formula is gonna be b minus a divided by n. How far I gotta go, divided by how many steps I'm gonna take. Will tell me how big each step has to be. Does that make physical sense? How far do I gotta go, how many steps I wanna take, will tell me how big each step has to be. Yeah, I like it. So if I wanted to go to the podium in 2 steps, I don't think I can take a big enough step. So maybe if I made it 6 steps, I might be able to do it. And then I can figure out how big each step has to be to get there in 6 steps. Okay. So it's a very physical reasoning behind that formula. So in our case, it's going to be 2 minus 0 divided by 4. 1. Okay, I like it. So I can go ahead and add that in on my picture. So if I'm using left endpoints, the first rectangle is going to go from what to what? 0 to 1/2. And the height of it is dependent on the first endpoint's height. So how tall will the first rectangle be? So the rectangle is going to go from 0 to 1/2, and the height is based on the left endpoint. 0. So watch as you draw. I really want this to make sense. How tall is the left endpoint of this rectangle if it starts at 0? Well, what's the output of that? 0. So how tall is it going to be at 1/2? A quarter, yeah. What's at 1/2? How tall is it right at 1/2? How do you figure out what this is? What's the height? Isn't it 1/2 squared? Yeah. Okay. So let me throw a little bit of more formality at you. This is the first left endpoint, correct? We're going to call it x1. This is x2. This is x3. This is x4. Drawing them in should not be bad because all you do, I drew the first one in. Now find the height for the second one, draw it in. Find the height for the third one, draw it in. Find the height for the fourth one, draw it in. So will this result in an overestimate or an underestimate?
Underestimate.
Big time underestimate, right? When we do the right endpoints, can you think ahead? Will that result in an overestimate or an underestimate?
Overestimate.
Yeah, I'm going to be over the thing the whole time. Okay. So when I go to draw them in, that's all I have to do. Is if I'm doing left endpoints, I find the first place, and I say, how tall are you? You're here. Bam. Next place there. Okay, there. Bam. Next place there. Bam. So drawing them in should be pretty straightforward. Now, can somebody tell me the area? So the height is f of xi. Right? x1, x2, x3, x4. Is everybody cool with me writing xi there? Is that cool? Because is that a constant? No, it's x1 and then it's x2 and then it's x3. So can somebody tell me what I goes from to in this case?
1 to 4.
Yeah, it goes from 1 to 4. Makes sense. 1, 2, 3, 4 rectangles. Yay! So I is sort of like the thing going from one rectangle to the next. Yeah, I like it. All right. What's the area? Well, the first rectangle. What's the area of the first rectangle? 0. I like it. What's the area of the second rectangle?
1/8.
Well, tell me what you did.
Height of 1.
I like it. So it's the height times the width, yes? And that's ground shaking, yes? For rectangles, height times width. Holy shit. Okay. What's the height?
1/4.
1/4, 11. F of x2, yes? Times the width. So try to, it's interesting trying to figure out how to teach this. I want to try to do it, bring you a little formality in the middle, but all I'm doing is finding areas of rectangles, but I'm trying to introduce some of the notation we're going to use. So what's the height? It's going to be 1/4 times the width is 1/2, 1/8. And here I can see the same thing. The height was 0 times the width is 0. Okay, right. So what's the third rectangle?
1.
So what's the height? What's the height?
1.
1. What's the width?
1/2.
1/2. There you go. Cool. I like it. And what's the fourth area, fourth rectangle?
9/8.
That'll be 3/2. I got going to 2, but that's fine. What is 3/2 supposed to be?
3/2 squared is that
9/4. Is everybody cool with that? 3/2, you go up to 9/4. It should be a little bit above that, but no, not a perfect graph. Too bad for me. Yes. 9/4 is the height, and the width, of course, is always 1/2 for this problem. 9/8. So how do I figure out my underestimate for that area? What do I do with those areas?
Add them.
Add them up. That's it. Okay. Let me see. Well, I can do that real quick. So my area using left endpoints is 0 plus 1/8 plus 1/2 plus 9/8. That's 7/4. Is that like that? Anybody do that yet? No? Yep. 7/4, otherwise known as 1.75. Okay. Now. This is where I wish. Well, let's see. Can you do this? Come on, Red. You can do this. Now let's go back in and do right endpoints. Yes. And you're all like, God, this guy can make freaking areas of rectangles hard. I'm sorry. So, just to let you in on like the teaching process, I could have done this without any of this and just said find the area of the rectangles. But I want to bring in the notation immediately, so later you can see how it connects. But each of these is just based on side, based on side. That's all we're doing. Yes? Each time. Okay. So what about right endpoint? So if I draw that in, the beautiful thing is I've already kind of got my height. So here's the first rectangle, second rectangle, third rectangle, fourth rectangle. Right? And then I just find the areas of all of them. Yes? So if I do, let's get rid of you, Red, sorry, Mike. Do right endpoints. Let's kind of formalize this a little bit. Aren't I, every single area we did, doesn't it look like this? Right? And I'm just letting I go from 1 to 4, right? what this book does. But obviously, now that I'm using right endpoints, this is going to be x1, this is going to be x2, this is going to be x3, and this is going to be x4. So now that I've shifted using right endpoints, does that make sense? Now the right, this one is going to be the first thing I use, so forth. Are you guys with me? There's a couple different ways to do this, but I think this book decided to do this. I'm not going to fully formalize this yet. So this will be the area of the ith rectangle. And again, the language I'm using is harder than the actual thing I'm doing, right? Just finding areas of freaking rectangles. So what's the area of the first rectangle? It's going to be f, it's going to be 1/2 squared, right? So 1/4, that's f of the evaluated at the first point, times 1/2. But for this problem, it's just 1/2, right? And of course, you realize we've already done this, yes? You guys see that? I mean, this rectangle is really just this one from earlier. So what's area of the second dude going to be? Isn't it going to be just this guy? You guys see that? So the second dude would be this guy, which is going to be 1 times 1/2. Right, which we already did. So what's area of the third one going to be?
9/8.
It's going to be this guy. It's going to be 9/8, right? We already did it. So it's going to be 9/4 times 1/2, which is 9/8. And then the new one is that last dude that we didn't do last time. This big ass rectangle here. And that's a beautiful one. What's the height? 4 times the width? Yeah. So what's our right endpoint area approximation? Force, let's see, force 11 force. Is that right? I really want you guys, on one level, all we're doing, if we draw this, we can just ignore it. We can just find the areas of each rectangle that we drew, right? And then add them all up. That's fundamentally what this process wants us to do. So if I add all these up, what do I get?
3.75.
Yeah, I get 11 force, which is 3.75. Okay, I like it. Now let's do midpoints. Oh, shit. All right. Let's see green. I know you're almost dead, but let's see if I can just get a little more use out of you. I don't know, it's getting a little messy. It's getting a little busy. Let me see. Yes?
Sorry, could you clarify like the difference between drawing it from the left endpoint and drawing it from the right endpoint?
Yeah, so in blue is the left endpoint. So what that means is, I know I'm going from 0 to 1/2. The whole question I don't know right now is how tall is that rectangle going to be? It's in this case, the left endpoint is going to be whatever the function is at 0 on the left side, and at 0 at 0, right? So the next rectangle was as tall as the output of its left endpoint. 1/2 squared is 1/4. Bam. So when I do right endpoint, now the first rectangle is going to be as tall as it is at 1/2. So that's why the first rectangle was there. It's 1/4 tall, right? And that's why when you do left and then you do right, you see a lot of repeats. Because the middle 3 are going to be this guy's first 3. I don't know if that makes sense, but that's a nice, quicker way to do these. Okay, I like it. Now, remind me again, this one, how is this related to the right answer? Too big, too small? Too big. That's the one that went over. And this one obviously is too small. We could right now do what with those things to make... Take the average, 11. Right? So what is the average of 11? 3.75 and 1.75. 18 fourths, 9 halves, 9 fourths. So 2 1/4. 2.25. Damn. Well, of course, Jeff, just 2.75, just look at it. That's fine. What did I do in my head? 18, 9/2, nobody knows what you did in your head, Jeff. Oh, I see, oh shit, all right. So the average we get is 2.75, when I average those two. Oh, I really want you with me. I know, yes?
When you average it, what do you do? Are you so, like?
Well, why does it make sense to average these two? Why does it just make sense?
Because it's a left.
Not just because it's left and right, but because I know that one was an underestimate and the other one's an overestimate. So if I average them, the answer I get has to be closer to the right answer than either one of those things. Does that make sense?
Yeah, so what you're doing, you just add them together divide by 2?
Yeah, add them together, divide by 2. That's how you average any two numbers. I love it. Or in this case, you can just eyeball it. What's in between 3.75 and 1.75? 2.75, yeah. All right. Now, I really want you with me. All right, now let's try midpoints out. Exciting, holy shit. And again, I really want you to start realizing what's controlling everything. I'm gonna redraw the picture because it's getting a little rough. And I'm gonna take this away because we know this. Okay, let me redraw the picture. Well, let me, that's right. Make everybody happy. There we go. So I want that area. And now I'm using midpoints. So the first rectangle is still going to go from 0 to 1/2. And I know that because my width and everything is still the same. But now the height is going to be based on the midpoint. What's the midpoint of that first 0 to 1/2? What's the midpoint? Yeah, 4. I like it. So that'll be there. So you see how the midpoint basically does this, roughly? Now my next triangle, I love it. My next rectangle is going to go from 1/2 to 1, right? Same way this did. So no matter left, right, midpoint, whatever thing you're doing, the rectangle is going from this to this every time, whatever that is. 0 to 1/2 in this case. It's just the height is dependent on the left one or the right one or the middle dude. So what's the height of this one going to be based on?
3/4.
Yes. Let me put it down here. So then I can do it, I can estimate it on my picture like that. And then from 1 to 3/2. So you can do 1, 4, 2, 4, 3, 4, 4, 4. So this is going to be 5/4. So that's going to be x3. So about right here. That's how tall that rectangle is going to be. So how do you draw the rectangle? Well, if you're using left endpoints, you go up to the height of the left. So I'm doing from 1/2 to 1. I'm going to go up to there, and there's my rectangle. If I'm doing right endpoint, I'm going to go up as tall as the right side of my rectangle. And if I'm doing midpoint, I'm going to go up as tall as the middle of the rectangle. So there are multiple ways to draw my rectangles in, but all I care about is what's the base, what's the height. And what's the height going to be is dependent on which method I'm using. So let me make this really clear. X1 is 1/4, X2 is 3/4, X3 is 5/4. So what would your guess be for X4? Holy shit. All right. So you can also start to see patterns. Sometimes it makes it quicker. 7/4. So what we do now is exactly the same thing we just did, except we use those to figure out the height. So let's do it one at a time. The area of the first rectangle is going to be the height times the width. So it's the output at 1/4, that's the height, times the width, which is 1/2 for this whole problem, right? And what's 1/4 squared?
60.
So you get 1/32, right? How are you doing over here, little dude? You alright? It's way over there. I know. That's what my camera sounds like. All right. So what about the second rectangle? It'll be f of what?
3/4.
3/4 times 1/2. 3/4 squared times 1/2. 9/16 times 1/2 is 9/32. Is that cool? Third rectangle. You guys, I mean, didn't I do exactly this every single time? What's the 1/2 isn't changing, of course, right? Because that's how wide each rectangle. The only thing changing is what I'm considering the height of the rectangle to be. So what's A3? It'll be f of 5/4. That's the height times the width. 5/4 squared is 25/16 times 1/2 is 25/32. Is that cool? Okay. And then the fourth area, f of 7/4, right? Is that 7/4? 49/16 times 1/2 is 49/32. So what do we get for the area of the midpoint? Using the midpoints to add all that together. 35, 84, is that right? 84/32? Is that right? I don't know. 50, 75, 84. And 84 divided by 32 comes out to be 28/11 almost. So, somebody save me for myself, please. 2.625. Which is pretty close to, not crazy close, but it's pretty close to this, right? But it's not the same as this, is it? Okay, I like it. Yes?
So is the height just an estimate?
No. Every single time I got a height, didn't I get it from plugging that endpoint into the function? Right? So to do this first rectangle, I use the midpoint, which is 1/4. How tall is it? F of 1/4. No estimate. You just plug it into whatever the function is they gave you. Okay. So again, fundamentally, all I'm doing is setting up the rectangles and then finding their areas and then adding them up. Right? Thankfully, we're never going to go to like 20 rectangles. We will go to infinite rectangles, but there will be a very nice way to do it where we don't have to find the area of each rectangle. Okay. So let me do this. Yes. So everybody's got their sheet. Let me know if you don't have this sheet from last time.
Is that from today or?
From last time.
Oh, no.
You got? Oh yeah, you need. So what I want you to do, yes, I'm sorry. Oh, you need one. What I want you to do is to try out. So let me know if you don't have this. It's the one with all the upside down parabolas on the back. Everybody sees the function I gave you? Yes. I've drawn the graph for you, being very nice. We did just try that out this semester. I'm using how many rectangles? Holy shit. So I want you right now just to try to draw the rectangles in. What am I going from to? From x equal what to x equal what? What's it tell you? I'm going from x equal what to x equal what? 4. 1 to 4.
It's just reading though.
That's right. So try to draw in. Just draw it in. Don't do any calculations. Just draw it in. and then I'll catch up to you. If you have no idea what the shit, if you're like, I don't know what this man said today at all, I wish he would speak English, that would be amazing. Then just hang out for a minute. Or, call me over you.
Repeat the left one.
Well, what's the
The first one is left.
yeah. What did I? Oh yeah, they're up there. All this very explicit. Yes. Calculator. You're gonna come later. See, when you go to draw it, you don't have to be very specific. You don't have to know what the height actually is as a number, right? You just got to draw the rectangle in. Let me catch up a little bit. What do you guys get for the width? Because if your width is wrong, the whole thing's going to suck.
1/2.
So it'll be 4 minus 1, right? B minus A. So 4 minus 1 divided by the number of rectangles, 6. 3 6 to get 1/2. So my first rectangle is going to go from 1 to what? Yeah, 3/2, 11. 1.5, 3/2. And I'm using left endpoints. So again, this very first step of just drawing the picture should not be any stress at all. How am I going to draw? If I started the 3/2 and I started the 1 and I start drawing up, where do I stop? As soon as what the line I'm drawing hits the curve, because it's left endpoint, correct? So how tall is it going to be? However high 1 goes as an output. So there's the first rectangle. If I want to use right endpoints, I would have based my height on how far that goes. That's it. All right, keep going. Draw the rest of them in. Look somewhat like that. Maybe your rectangles are, actually straight and stuff, but right? Do you guys see? Did I use that as a height? Did I use 4 to tell me a height of anything? Why does that make sense? Because the last rectangle ends at it, and it's a right endpoint. It's not used here. So sometimes people, all right. I'll get it. So let's do this. See what I've written here? how many of you guys have seen the notation here? Obviously the f of xi, we've seen that already. Delta x, we've seen that already. L6 just means the left endpoint with 6 rectangles, right? Has anybody ever seen this notation? Yeah, where have you seen it before? Pre-calc maybe? Okay. Programming class, kick-ass. Anybody ever taken statistics? If you've taken statistics, you know that for damn sure, right? Because there's a ton of formulas that have that dude in it. Can somebody tell me? In one word what this symbol means? Sum. I love it. SUM, right? Just in case some people have no idea what it is. Like some what? Something. No. So let's focus on that for a moment. And you know, it kind of makes sense because what do I do once I calculate all my areas? Don't I just add them up? Okay, so. All right, so what that symbol does for us. So let's investigate this symbol. Let's see what the shit this means. So if I have something like this, what is, can you, for those of you who have never seen this before, can you see what this is going to be beautiful grammar. Can you see what I is doing? What do I be doing in that problem? What is I's values? What do you think?
It'll be increments of 1.
It starts at 1. And it works its way to 3. So what's I doing? 1, 2, 3. So what this means, this symbol means sum. I want to sum up this. But what is this doing going from 1 to 3? So what this whole thing means is add I to itself repeatedly as it goes from 1 to 3. So when I is 1, that's 1, plus when I is 2, that's 2. Plus, when I is 3, that's 3. So that'd be 6. Amazing. That's crazy. So what about this? Let's see what this means. So in this problem, what is I doing? 2 to 5. So it's 2, 3, 4, 5, 11. So when I'm using the summation notation, I'm understanding that, and one little reason we use I here a lot is because this is called the index of the sum. It's just the word we use. The index tells me what the variable's doing, and that's always known to be a natural number. Or it could be an integer, to be honest, but a whole number, normally positive. So all this really is it's like a combination of function notation with addition. So when I is 2, what is this?
2.
Yeah, I get 2 squared minus 2, 4 minus 2, 2. Is that cool? Just plug a 2 in. So that's the function notation part. I is a variable, and you know what the expression is, I squared minus I. So what if I is 3? Yeah, you get 9 minus 3 is 6. I is 4.
12.
Yeah, 16 minus 4 is 12. I is 5. That's as far as you got to go, right?
20.
20. And then you just add that shit up, right? And you get
40.
40. So again, it's a very concise way to say, add up all the outputs you get for I squared minus I for I equal 2 to 5. That's a very quick way to say all of them. Yes? And that's basically what mathematicians do, is they have this huge thing, do this and this and this, and then we're like, let's make that like 3 symbols, right? Shorthand that thing, right? And then everybody throughout history is like, I got to catch up with what the hell these people did. Yes? So it is learning a different language, it totally is. How do you guys feel about this? I mean, this by itself, you're like, give me a bunch of problems like this is what I hope you feel like right now. These problems right here by themselves, nice. You just throw a bunch of shit in and then add them all up. I mean, what better problem could you hope for? All right, now of course we're going to use it in worse ways, but nothing quite this simple. Too bad for you. So, if I want to capture what I've been doing so far, if I write this, is this cool with you guys? This is what we've been doing so far. The first area plus the second area plus the third area, all the way up to the whatever the nth area, however many rectangles, right? Wouldn't this be, yeah, other end. Does that become this? Think backwards. Does this become that? When I is 1, that's A1. Plus. When I is 2, that's A2. Plus. When I is 3, that's A3. Plus. Up to AN. Are you guys cool? And what is this? How do we figure out the area of each rectangle that we've been doing? It'll be the width, right? The width times the height. And we actually kind of build, here's the one little weird thing about this. We build this sort of like it's based on left endpoint. But again, that's why this book kind of does a little bit of liberties with things, that's all right. This is why the X1 had to shift over if we're doing right and maybe. So it's the height of each rectangle and the width of each rectangle, right? So what's the ith rectangle's area? That's how you say this. It would be the ith rectangle's height times its width. And we're assuming the width stays the same, thank God. So then what's this? The sum, I equals 1 to n, f of xi times delta x. Height times width. So we don't lose the idea of the rectangles. You can see them, height times width. And we're just adding them all up. Okay, I like it. I love it. I like it. I like it. Okay, so let's come back to this. Any questions on that? I really hope you saw how we got there, and now you can read this. Add up the areas of the n rectangles. That's what that says, right? Okay. So let's try to be a little more formal, which is what everybody loves with this problem. I love it when I hide. There it is. Past Jeff just likes to mess with the rest of you. Okay. We've got our rectangles drawn in, but let's be a little more formal about this. F of xi would be negative xi squared plus 6xi, not plus, okay, minus 4 is that right? Yeah, okay. Does everybody see where I got that from? F of x is blah 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 with x's in it, so f of xi is blah 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 with xi's in it. Times 1/2. Now let me ask you this. If I had, what I'm about to do is not necessary, but my God, do it, right? If I had to add up a bunch of shit in every single one of them, so if I had to add up, and I know you can't see this, people at home too, but if I had to add this up, let's do this. 1/2 times 5 plus 1/2 times 11 plus 1/2 times 15 plus 1/2 times 30 plus 1/2 times 10. Couldn't I take a 1/2 out? So then I don't have to deal with fractions. You guys see that? I can take a 1/2 out. Of course I can. It's a GCF, right? So isn't this basically saying that? Isn't this a big string of plug a 1 in, plus, plug a 2 in, plus. So what's going to be in every single term? Freaking 1/2. So watch this. Can't I factor that stupid thing out? Can't I just bring it here? And that always works that way. Sorry. Zoom out a little bit. So just take the 1/2 out. Now I can focus on this. So now this just becomes 1/2 times, put a 1 in, get a number, plus, put a 2 in, get a number, plus. Do you guys? So I'm still calculating the areas of the rectangles. I'm just doing it a little more cleverly, right? I've taken the stupid width out because it's in every single thing. So what do I get when I put a 1 in? Enter 1. Say again? 1. You get 1? -1 plus 6 minus 4, yes. 1. What's the next number I have to put in?
1.4.
Now let me be careful here. Oh good, I'm doing right. So be careful. What's x1? 1. What's x2? 3/2. I like it. Now I really want you guys to be with me. This is a really simple mistake to make. Does it say I here? Does it say I? Does it say I here? No, it's not I squared, is it? It's xi squared. So we've already identified, right, what my x stuff is. x1 is 1, x2 is 3/2, yes? x3 is 2. And you can just march down your picture, yes? So now I'm going to plug a 3/2 in, yes? Now, just to remind you, oh boy, throwing a lot of shit at you. Everything we're doing right now, based on areas of rectangles, sounds great. Yay! Then I have to come in with notation and all this stuff. Ah, boo, but it's still the same idea. So now all we're doing is figuring out the height by plugging stuff in. I want to remind you something really neat about your calculator, right? Let me remind you this. This is going to save your save yourself from yourself. Let me remind you. What's the function that we're using right now? Negative x squared. What was it? Squared, Jeff. You do, buddy. Plus 6x. Is that right? Somebody help me out. Minus 4. What was the quick way to get the calculator to tell me a bunch of outputs? Table. And you can be really smart about it. Watch this. See up here, table set. Go to table set. I want to start at 1. You guys agree with me? And now look, delta table is actually delta x. What's delta x again? 1/2. So make this 0.5 or 1/2 if you don't understand that. So now if we go to my table, look at that shit. Gaze upon the shit. Yes? Sorry. So, you guys with me? I mean, that's insane. I mean, come on.
Wait, so what about like infinite?
Auto.
Make it auto. Yeah. You could make it ask, but then you have to plug all these in. But I would every time make it auto because the delta table is the delta x. No matter what your width is, that's when you make the delta table. It's almost too nice to believe, right? So now, you guys all have that list? Yes? So now, if I go back, Jeff, you gotta go over here. You gotta do this. No, you gotta go that way. Okay. Sometimes. Oh, good. So now I can just copy from there. Plus 2.75, right? Plus 4. I just gotta make sure I stop the replacement. 4.75 plus 5 plus. Where'd you go? 4.75. 1, 2, 3, 4, 5, 6 rectangles. Do you see that? When I show this nice table thing to people, they go too far. Just take a second, make sure you got 6 heights, because you're supposed to have 6 rectangles, yes? So you don't go too far. And now you just got to throw that on the calculator to see what the hell it is. 9, 10. Oh, yeah. Are we going to try to do that? I don't know. 9.5. 19.5. 22.25. 11.125? Is that it? We'll see. I don't know. Anybody got it though?
11.125.
What is it?
11.125.
Look at Jeff. A math teacher able to do math. What? All right. Now, real quick, do you guys think that's an under or an overestimate from your picture? Definitely under. It does go over just a little bit, but nowhere near enough to cover all the under it did, yes? So if we did do the right endpoints, now watch this. Here's another shortcut for you guys. I really want this to make nothing but sense. What was this from? Can somebody tell me what that one right there represents? There. What's that one right there? What does it represent? You can do it. Come on.
First rectangle?
What about the first rectangle? Be specific.
The height.
The height. I love it. Right? That's what we got when we put a 1 in, x1, into the formula, yes? What is my first rectangle height going to be if I use right endpoints? If I use right endpoints, the first rectangle is still going to be in the same place. It's just the height's going to be determined by the right endpoint, yes?
2.75.
So now the height's going to be 3/2, yes? And then the next height's going to be 2, and so forth. I don't know, not the height, sorry, but you're going to plug a 3/2 in to get the height. Are you with me? Plug a 2 in to get the height, just like we did here. I really want this to make sense. So watch. And what's the, am I going to use 4 now for a height? Am I going to use 4 to plug? Yes, I am, right? So let's do this. Really, this is so awesome. Can you take a second and try to draw the rectangles in? We're using right endpoints now. So let's put in all of our points, because I know the width is 1/2. So again, I'm using 3/2, 5/2, 7/2, stopping at 4. I really want to smell one. Remember here, I started at 1 and I drew and I stopped when I hit that and went over. Well, now I can do this. 3/2, go up, stop, go back. There, right? Now the first rectangle height is going to be based on the right endpoint. Does that make sense? Just drawing this crazy ass thing in, it's going to be, the height is going to be based on where this guy goes. So go where that guy goes. There's the first rectangle. And then just keep going, keep doing that. Gee-haw. Woo. Maybe be a little more fun. You don't have to be perfect with this, it's just supposed to tell you a rough estimate about whether it's an over or an underestimate, right? This is obviously going to be an overestimate, yes. Now, here's the shortcut I really want you guys to understand. Which height in that list of heights up there, which one are we not going to use? 1. We're going to use all the other ones, plus what we get when we plug 4 in. So watch this. This kicks so much as I threw my, thank God I didn't throw it anybody's that one. So now, this is going to be 1/2, that's the width, right? That's the width that we factored out. And I just start here. 2.75 plus 4 plus 4.75 plus 5 plus 4.75. And now I just need the next height. Because now I'm actually using 4 to get a height. So you can look at your calculator. 4 goes to 4. Now I just need to do that. Let me see if I can get it real quick. What do we have? Of course, that's 3 times that's 1.5, so that'll be 12.65. Yes? So that's an overestimate. That's an underestimate. So to get a good estimate from just these two things, I can average those. And if I average those, 0.75, I should get 11.875. Yes? Look at Jeff doing numbers. Now, last thing I'll show you today, I think, because I've really thrown a ton of shit at you. Oh yeah, true. Actually, let me No, that's right, it's a little freaky. And that's basically the same thing we just did. Okay. I want to show you how to check your work in the calculator. But before I do that, I want you folks in this way just for a second. Come here. I am talking to my phone, but that's the normal thing, right? Okay. So this process here. What does this process here do?
Some of the areas.
But what does it do? What's the result mean? You do it.
Area of the function.
Area?
Under the.
Under the function from something to something, right? Okay. How did we say we would improve this? How do you improve this? Well, if I use 4 rectangles, I can improve it by using 8. How do I make it perfect?
Infinite.
So again,
Infinity.
infinity. How will we do that? Can I just throw an infinity in? Can we ever put an infinity in anywhere? Those of you who still are doing that, stop. You can't do that shit. You can't put infinity in. You come show me infinity, right? Which is what I think was in the suitcase in Pulp Fiction. Oh. Find that suitcase, show it, oh, and then I'll let you put infinity in somewhere.
That suitcase, do we get an A in class?
Find exactly that suitcase. And then we'll, I gotta cover my ass because you might know somebody who knows somebody. I don't know. So what I do to make this perfect is I just do this. I mean, what does that mean? Now that was easy, right? I just wrote something. But 5-2 is gonna be doing this by hand. Yes. Now, watch this. This is so cool. Let's see if you guys remember this. This is a big step. What's going to happen to the width of each rectangle if I let the rectangles get more and more and more? What's going to happen? I started doing it. They're going to get smaller and smaller and smaller until they get to what? Who remembers what delta x does if I let that go to infinity? And it goes to what specifically? It doesn't go to 0. What do we replace delta x with? No? dx. Remember that? Big step in x is delta x. Infinitesimally small step in x is dx. This is going to become that. Because now, it wasn't xi can actually be any point in the rectangle. We use left, right, midpoints, and to be honest, you can use any point. And if I make this go like this, how many choices do I have? One choice. So that's just one choice for us now for that. And this, the symbol that was chosen is this symbol. I've just overdone it there just for dramatic effect. But it's really just the letter S stretched. That's literally all it is. Because what is this? This is the Greek letter S. Because it's a sum. So we went, oh, all right, let's use S. S? Let's make it look weird. Okay, stretch. So anyway, sorry. I'm sure, I think poetry and mathematics, they were probably on something when they created it. I'm not saying you should be on something to do it. I'm not advocating for that. I'm not saying that. Maybe. And then, this is a bit, I just want to, and then here's where it would be from A to B. From A to B. So it's a lot like this, except now this means the interval that we're, okay. Now we're going to go over that a little more slowly tomorrow, but I just want to show you that this symbol is nothing to be scared of. It's just a big ass S, because it means sum. That's what it really means. So now watch this. This is so cool. Here's the way you guys can check your work when you're doing these sums. Do I have this? Yeah, I do. So it's in there. Let's graph it. Let's all do Zoom 6 so we all have the same graph. All right, now, I want to calculate something with this, right? I want to calculate the area, right? So I want to go up to where it says calc, right above trace. We've gone there a few times. And by the way, nobody's ever, I can't remember anybody saying, look at number 6. Sorry.
How dare you?
Real quick, if I hit number 6, I can then pick any value for x, and it will tell me the slope there. So it's 0 at 3, obviously, right? Anyway, so go to second trace, and look at the very last dude. Isn't that what we just introduced? So that is basically the infinite sum, letting rectangles go to infinity. And what it wants from me now is, what does it go from to? In this problem, what did it go from to again? 1 to 4. So from 1, enter, to 4, enter.
Hey, how do you answer that?
You just pressed it.
Say again.
Oh,
What did we get, by the way? Where's my, okay. Oh yeah, so we got 11.125, we got 11.875, I'm sorry, 11.125, 12.625, and we averaged them and got 11.875, right? And the actual answer is 12. So with 6 rectangles, we got really close. So that's what you get if you use an infinite number of rectangles. And 6 was enough to get pretty damn close, yes? Why do you think it only took 6 to get pretty close? Beautiful. It's a well-behaved function. It's just a prep, right? What if I had some crazy ass thing that, then I might need a lot more rectangles to get a better approximation, but most of the time I'm going to use well-behaved functions. How do you guys feel about that? Is that right? So there's a beautiful way to check your work, right? It's never going to equal the same thing you get there, especially if you use less rectangles, you have a freakier function, but it should be kind of close. Especially if you use midpoints or you average left and right, yes?
We're gonna have to do this for trig functions?
Yeah. Yes. I mean, real quick, if I had given us like sin x, what's the only thing that does to me is I plug it in there to figure out the height, right? That's all it does at the moment. Now, don't you want a shortcut to this? The same way we wanted a shortcut to the limit definition of derivative, yes? And we did do shortcuts. This one we're not going, no, I'm joking. We will get to a point where there will be a shortcut, and it's going to be involved with proving that this is related to the antiderivative somehow. Right now, there's no freaking reason in hell we would think that this is related to the antiderivative. But it totally is. So derivative tells us slope. We're going to prove that the antiderivative, what am I drinking? The antiderivative gives us area under a function. Okay, and I think that's plain. All right. Do I want to give you this? No, it's too soon. Too soon. Okay. So next time we'll get into 5.2, which is where we'll be calculating areas and letting the number of rectangles go to infinity. We'll be doing that by hand. Sounds really exciting.